Oh, okay. So how do I use it? Hello? Okay. All right. So
It's 9.
it's 9 now. Okay, well, thanks for everybody coming. We're here today to see the Master's Defense presentation of Iskandar. So Carrie Ann Johan Iskandar, known to everybody as Iskandar. So just very briefly, he's going to talk about Mantle Xenoliths of Harrat Uwayrid. And I just wanted to mention that, you know, getting fragments of Mantle in your hand are very difficult, you know, obviously, because they're at great depth. So the moho is about, 35 kilometers or so in the continents, and then about 6 to 7 kilometers in the ocean. If you're lucky enough to be on an international drilling program to drill into the Mantle, you can get fragments from there. And also, of course, the base of ophiolites, and Saudi Arabia has many ophiolites. The problem with working with these is that they're extensively serpentinized because of the hydrothermal system associated with oceanic regions. In stark contrast, Mantle xenoliths from continental regions are exceptionally fresh, so they're very nice to work with. So when Iskandar came to me, I guess probably in 2020 or so, looking for a project, we agreed to work on this. So I hope you enjoy his presentation. And just as an aside, I'm wearing an Indonesian batik that my other master student, Thesis, was very thoughtful enough to pick up for me. No. Okay, so anyway, I'll give it over to Iskandar.
Thank you, Doctor, for the introduction. Check. Okay. Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Alhamdulillah wassalatu wassalamu ala rasulillah wa ala alihi wa ashabihi wa man tabi'ahum bi ihsanin ila yaumiddin. Good morning, everyone. I would like to greet everyone here. Thank you for coming in this morning. Special mention to our beloved chairman, Dr. John Humphrey. I thank you for your presence. Also to my esteemed thesis committee, Dr. Scott Wattam, Dr. Amau, and also Dr. Ardi. Thank you for being here. And also to my beloved colleagues from CPG and also from KVPM. Thank you also for being here, present here, and hopefully we enjoy today's presentation. Today I will be presenting for my thesis defense for a geology master degree, and the title of my presentation is Mantle Xenoliths of Harrat Uwayrid. So before starting the presentation, I would like to take 1 minute to briefly introduce myself and my thesis committee. My advisor is Dr. Scott Wattam, and we also part of the committee is Dr. Abdul Jamiu Olalekan Amau, and also Dr. Ardiansyah Ibnu Hidayatullah, and me myself, Dr. Johan Iskandar. Everyone knows me, familiar with me as Iskandar, as author of the study. This will be the outline of today's presentation, inshallah, and it's divided into generally 5 sections. Okay, introduction, literature review, brief literature review, methodology, results, and then discussion, and then closed by conclusion, recommendations, and brief acknowledgements. We'll start with the introduction. Okay, xenoliths are inclusions of mantle or lower cluster rock fragments brought to the surface by extrusive igneous rocks, and we can see an example of this in the image to the left. They are transported to the surface via extrusion of basaltic magma of predominantly alkali basalt of nephelinite and basanite compositions. And here I took from USGS image of the Earth, and we have here the interior of the Earth with its layers beneath. And I would like to focus on the mantle. The Earth mantle extends almost 3,000 kilometers, okay, around here, and comprise about approximately 83% of the Earth's volume. Ultramafic xenoliths are regarded as fragments of the mantle, okay, either the lithospheric mantle or the asthenosphere upper mantle here, represented by the light brown and dark orange color respectively. They are among the few means to directly observe the Earth's mantle. Therefore, their importance. Furthermore, the western part of Arabian plate has significant exposures of Neoproterozoic age continental crust, and which comprises the Arabian Shield, and is represented by the orange color in the map. Among the younger rocks that cut the Arabian Shield are Cenozoic age alkali basalts, fields known as Harrats, and these are the red color. These Harrats represent one of the large basalt fields in the world, and they extend from the north to the south, passing Syria, Jordan, the Kingdom of Saudi Arabia, and Yemen. These extensive lavas have been interpreted as volcanic products related to the rifting of the Red Sea. These Cenozoic age Harrats all contain abundant mafic and ultramafic xenoliths. Studies from various lava fields in Syria, in Jordan, Saudi Arabia, of course, Yemen, have produced insight to the characteristics of the xenoliths and explanations of the explanation of the Arabian plate mantle condition. The problem statement for the study is that large volumes of these xenoliths bearing Harrats lie within Saudi Arabia. A total of 12 Harrats have been reported in Western Saudi Arabia, and we can see by the red color, which with the green outline here on the map. 9 Harrats have been identified as containing xenoliths. However, whereas some are well studied, others are less explored. Published details of the xenolith studies are limited to 5 major lava fields, which are Harrat al-Birk, al-Kishb, Khaybar, Hutayma, and Uwayrid in the north. A significant time has passed since many of the studies were performed, and advancement in technology has led to improvement in analytical instruments and techniques. Opportunity therefore exists for the further studies of these xenoliths from these Harrats. And we chose Harrat Uwayrid xenoliths, although they are well studied. However, comprehensive bulk rock chemistry and additional mineral chemistry analysis are yet to be studied comprehensively. Therefore, the study has the following objectives: petrographic study to determine mineralogy and rock classification of the xenoliths in Harrat Uwayrid, bulk rock chemistry by ICP, OES, and MS to determine major and trace elements, concentrations of the xenoliths, and finally, mineral chemistry by EPMA to measure major elements of xenolith minerals. Okay, the study area, as mentioned, Harrat Uwayrid is located northwestern part of Saudi Arabia here, between the city of Tabuk and Al-Ula at the south. It is lying between the administrative division of the Tabuk region and the Medina. And as you can see, the body itself has 2 Harrats, which is divided by this small line here. And at the northern part is Harrat al-Raha, whereas our study area, Harrat Uwayrid, is located further south. Let's review a little geological background. Harrat Uwayrid is located along the western margin of Arabian plate, so approximately here. The structural trend of Harrat Uwayrid follows the or parallel to the Najd fault system orientation and the Red Sea axis here, and it has a value of north 30 degrees west. And the lower host lavas of Harrat Uwayrid, here with the black color, are underlain by Paleozoic age formation and has angular unconformity contact. Therefore, this suggests that the formation of the Harrats postdate the tilting events in the northern shield. And in this beautiful image here, we see the contact represented by the dashed white line, and probably here it's underlain by the Paleozoic sandstone of Sak formation. And here, potassium argon dating from Altar 2019 provided 2 age distinction for the Harrat, older and younger. The older one, starting from the older, being Upper Miocene, and the younger being Pliocene and Quaternary. This additional information, study from Dr. Watam in preparation, has managed to further specify the age and without specifying as Quaternary. And the older rocks in the northern and southern plateau lavas are exclusively of lavas of alkalic basalts, Hawaiites, basanites, and rare transitional basalts, whereas in the younger in the center are primarily scoria of basanite and characterized by bombs and laser lava flows. Okay, and this is additional information regarding the host basalt. We have the older and younger, and these are the representative thin section images, and also based on the chemical classification of the basalts. And here are the from the central area, and these are from the northern and southern area. Previous studies of xenoliths within Saudi Arabia amount to 12. Okay, and they are quite old, starting from Gent in 1980, which is monumental, along with Coleman, which identified the xenoliths. And here we see on the map to the right the number of times that the xenoliths were analyzed or studied in each let's say Harrat. Okay, and for Harrat Uwayrid itself, the study was started by Henjens-Kust in 1990, followed by Bulstajan in 1995, and then rather recent Kaliwoda in 2007 and 2008 respectively. And as I mentioned at the beginning, these studies have yet to address the whole rock chemistry in detail. Okay, the methodology of this study is briefly explained in this simple flowchart and is generally divided into 4 steps. Sampling through field work, and then preparation of the samples, analysis by microscopy, XRE and ChemScan, ICP, the mass spectrometer, EPMA, the probe, and the microscopy resulted in petrography data. Okay, and then ICP resulted in bulk rock chemistry, major and trace. EPMA resulted in mineral chemistry of the major elements. And finally, from this data, we interpreted rock classification, degrees of partial melting and melt extraction, metasomatism, oxidation state, and geothermal barometry. And finally, by including the literature study that we did at the beginning, we conclude with a final interpretation. So outcome from the studies that is expected, from the study are determination of the classification and comparison of the study results to other Arabian xenolith suits, a petrogenetic history of the xenoliths, and maybe a rough or general interpretation of the lithospheric mantle setting unit Harrat Uwayrid. And we immediately go to the results. Field work in 2020 with Dr. Scott and Mr. Mutasim. We came to 25 locations. This resulted in acquisition of 36 ultramafic mantle xenolith samples. From those, 18 representative samples were chosen for further preparation and analysis. And just again, as context, these are the images of the northern and southern lava plateaus, and these are the host basalts with the rare mantle xenoliths that were found entrapped. And here are the cinder cones, which are characteristic of the central area. And we can see that the majority of the mantle xenoliths are here, and these are the scorious features of the basalt. And here are the entrapped mantle xenoliths found in the central area. And these are the 18 representative samples that we did further preparation and analysis. And we can see the characteristics in these pictures, starting from the color and also their size. And we managed to establish classification with some as leurzolites, dominantly are rosolites, and in the middle Harzburgite, and few whorlites. Okay, so these are representative thin section images of the leurzolite. Okay, and the leurzolites are light to dark green in color. They exhibit protogranular textures, and as you can see here, olivines, clinopyroxene, orthopyroxene are present within the composition of the rock. And we have minor spinels, which are in the orange or brownish color in the PPL. And norm calculations from the major elements produce these percentages of the minerals. And these are next Harzburgites, which are representative images of the thin section of the Harzburgites. Samples are light green, and they represent the mineral, the dominant mineral, which is within the Harzburgite. This possess weak porphyroclastic and predominant protogranular textures. Percentages from known calculations of the minerals that are present, olivine, clinopyroxene, and orthopyroxene with minor spinels, are in this range. And finally, the Harzburgite possess relatively less clinopyroxene in comparison to the leurzolites. And finally, the least common type from the collected xenolith samples are the whorlites. They are in dark green color. They display porphyroclastic textures. And here from the image, we see that representative image that olivine and clinopyroxene are present in the samples, although very little to know. However, very little to no orthopyroxenes are present in the sample. So therefore, we come to the model mineralogy classification. This is a ternary classification from MITRE 2004, which classifies ultramafic rocks. And generally, they are divided into pyroxenite and peridotite. And here, our study, the Harrat Uwayrid study from the study, is represented by the green circles, whereas also displayed are peridotites from neighboring Harrats with yellow and red color circle, also overlain are massive peridotites classification of the worldwide outcrops from Bodinier, and also the general type of Western Arabian peridotites. Okay, and generally they are lying within the peridotite classification, and specifically they are divided into leurzolite predominantly of the Harrat, I mean, and some are Harzburgites, whereas we have minor whorlites here. And as we mentioned earlier, the majority of peridotites found in the Western Arabian are here represented by the black triangle and are leurzolites. Okay, this is a small figure, another ternary plot, which represents mineralogical trend from leurzolite to Harzburgite with the reduce of clinopyroxene, and this is synonym or corresponding to a mantle trend, which due to increasing or continuous partial degree melting of the leurzolite, they evolve into the Harzburgite, and that's due to the reduce or the melting of this clinopyroxene. And to further emphasize this, that the leurzolite here is considered as a fertile mantle, okay, and after undergoing partial melting, they will be depleted of melt, which is rich in calcium and aluminum oxide, and leaves the residuum of Harzburgite, which are dominant with olivine. And as we go further above in the trend of titanium against aluminum oxide, we find the composition of the oceanic basalt. So yes, we have here established by the scientists that leurzolites may evolve to Harzburgite with mantle extraction, and the melt itself are later on as basaltic compositions. Here are Harrat diagrams of major elements of whole rock chemistry. I would like to emphasize here in silica oxide that the content of silica oxide inside the peridotites here are, let's say, more than 90% below the 45%. So therefore, corresponding to ultrabasic classification, which is synonym to the ultramafic mineralogy classification. Okay, and more importantly, we have aluminum oxide, calcium oxide, sodium oxide, and titanium oxide, which corresponds nicely with magnesium oxide, and they produce this pronoun negative trend, which later we will discuss is related to partial melting. Okay, and additional information that LOI, or loss of ignition during the heating of the samples of the peridotites, are less than 1%, meaning that they have low volatile contents, which means that they are relatively fresh or extremely fresh. I mean, in comparison, as Dr. Scott mentioned, to other peridotites such as the abyssal peridotites in the ocean. Magnesium numbers, which is the ratio between the magnesium oxide and iron oxide, which is also a parameter for partial melting of the mantle, ranges from 88.2 to 90.5, which is similar to Western Arabia and worldwide spinal peridotite xenoliths. And yes, we'll skip it. So trace elements of whole rock chemistry here. Here are plotted on RE diagrams, normalized to carbonaceous chondrite values. Okay, and they exhibit two general trends. And generally, the REE are divided into two: the light rare earth elements to the left side of the REE, and then the HREE, which are the heavy rare earth elements, to the right side. And here I divided the two trends. The upper one has the show fractionated patterns with high light REE or LREE abundances, okay, ranging from chondritic to 1.5 order magnitude higher, and HREE, which are similar to the chondritic values. Whereas the second trend displays a flat pattern with LREE and HREE abundances similar to the chondritic values shown with the dashed line. Also plotted are the several or more variative trace elements onto the spider diagram normalized to primitive upper mantle. And here we have patterns that are relatively fractionated on the top and flat patterns on the second trend at the bottom, although generally they are still displaying values similar to the primitive mantle represented by the dashed line. We will continue with the mineral chemistry. Okay, for olivine, the phosphorite number, which is ratio between the magnesium and iron molecule atomic proportion of the olivines of most of the Harrat-Uwayrid peridotite xenoliths range from 83.46 to 93.05, and these are considered as peridotic by McDonald and Rudnick and others. And major elements composition of the olivines are generally similar, and we have the averages here. But pyroxene is an important mineral in peridotites. Why? Because they contain or a lot of the elements that are parameters for partial degrees of melting and others. Okay, and here Harrat-Uwayrid peridotite xenoliths clinopyroxene show similar composition to other Harrats. Here our study with the green circles are in similar position with Harrat Kish, Taima from Ahmed 2016-2019, Harrat-Uwayrid, the previous Harrat-Uwayrid of Kaliwoda study, Harrat Kish with the purple color, and also here the field from Harrat-Uwayrid from and other location from Henjen Kast in 1990. The exception should be Harrat Kish, I'm sorry, I missed this, which has higher chromium number, which this is the ratio between chromium and aluminum, again, atomic proportion of this clinopyroxene, which again is related to partial melting of the peridotite in the Harrat. And they all have comparable values with these magnesium number and chromium number values. Okay, and finally, for the mineral chemistry, we have spinel, which is very important, and this is considered as the alumina phase in peridotites. And the alumina phase in peridotites, they change depending on phase, depending on temperature and pressure. So the lowest pressure will be plagioclase, and here spinel will be the intermediate, whereas deep peridotites will have garrets in their position. And here the spinels chromium number and magnesium number fall into the field of spinal peridotites in global from McDonald and Rudnick 1998. And also they are classified as fertile mantle rather than only one which are refractory or considered refractory mantle as product of partial melting. And we will start the discussion. So the first analysis that we conducted is the partial melting, which is commonly or mostly undergone or subjected by onto the mantles. And here we use a bivariate plot of aluminum oxide and calcium oxide of the bulk or the whole rock chemistry. And here we have degrees of partial melting, 1 to 20%, and we have varying results or quantific numbers for the degrees of partial melting of Harrat-Uwayrid peridotites, for approximately 1 to 17%, and we can see from the table here. Also, we did similar analysis using the relationship between phosphorite of olivine and chromium numbers of the spinel, and is known as the osmo-olivine spinal mantle array by RI. And we have the degrees of partial melting quantified in the middle here. And we see from this mineral chemistry that we have similar numbers, whereas here it is between or approximately between 0 to 13%, although we have an outlier here, which is 30%. And we will validate this later. All of these values are interpreted by a formula, okay, which calculates fractional melting or partial melting from Helbrand 2001, and they have similar, although relatively less percentages, and this validates the outlier, and we see that the outlier actually is the result from the whole rock chemistry with 4%, whereas the others are high. We won't mention, or we have not analyzed this, and we will not discuss regarding this further in this presentation. Still regarding degrees of partial melting, here are the peridotite of Harrat-Uwayrid plotted on a global peridotite trend, and here we see the primitive mantle values, and these are the highest degrees of partial melting, and we see that partial melting of the Harrat-Uwayrid is low or categorized as low, and in the middle to moderate degrees of melt extraction or partial melting. We also calculated oxidation state of the peridotite and oxygen fugacity values range from minus 1.89 to minus 0.22 delta log FO2 and plotted below the FMQ buffer. And this result suggested that the peridotites originated from equilibration in reduced environments. And furthermore, the Harrat Uwayrid's Xenoliths fall into the primitive mantle nicely, whereas the Habsburgite, which are fall or inside the field of abyssal arc peridotite, which are characterized with slight metasomatism. Geothermobarometry, which was also performed, calculation were also performed. Temperatures that we got were between 1000 to approximately 1135 degrees Celsius. And also the pressure that we calculated were between 1.72 to 3.76 gigapascals. And this corresponds to depth, between 50 to 105 kilometers. And this, we see the depth of the Harrat Uwayrid peridotite xenoliths in comparison to the Kaliwoda study in 2007. And the final interpretation that we did was metasomatism that was found in the peridotites. McDonald showed that continental lesophotic mantle is generally characterized by enrichment of incompatible element, and this is the definition of metasomatism. So metasomatism is the enrichment of the mantle by certain agents, fluids, and the characteristics are well exhibited by the peridotite xenoliths of Harrat Uwayrid and other Western Arabian peridotites. As we see here, the LREE are to the left side, and we can see here the abundances of the LREE, whereas the depleted mantle should have depleted LREE due to LREE being incompatible elements, which partition or prefers partitioning into the melts, into the liquid, rather than the solid phase. And the peridotite xenoliths from the young Harrats are less than 30 million years, record degrees of enrichments which are slight to pronounced. And this is also a table which represents or show metasomatism. These are chondritic values, and this is parameter for LREE, and we see everything that is above the chondritic values are considered as enriched or metasomatized. And three agents usually cause this metasomatism by Downs 2001, yes. But from the three agents, which two of them are silicate melts and carbonated magma, we do not see the evidence for these agents here. And therefore, fluid containing H2O is the most probable agent, and this is confirmed by studies of Bluestagen and Kaliwoda. Finally, this is cross-section of the mantle, of the interior beneath the Arabian plate from Maguire 1988. And we see the Harrats, and approximate Harrat Uwayrid position is between Al-Birk and Al-Kishf. And we see here that the xenoliths don't have any particular cluster. We see the Habsburgite, they are distributed nicely from the top to the bottom. Also, the Xenoliths are here, and the yellow outline on the Habsburgite show enrichment, and the enrichments also are distributed evenly or nicely from top to bottom. And the let's say the negative of peridotite of xenoliths are they are extracting random mantle fragments, so we do not know exactly where they come from, but we just try to visualize these xenoliths, and we know that they most probably took fragments from the lithospheric mantle and the upper mantle respectively. And finally, we reach the conclusion and recommendation. Harrat Uwayrid peridotite xenoliths are identified as spinal rhizolite, Habsburgite, and whorlite. No distinctive feature are apparent between the xenoliths retrieved in the younger area and the older area. And the peridotite xenoliths of the study have low to moderate degrees of partial melting, ranging from 1 to 17%. The oxygen fugacity of the xenoliths range from 1.89 to minus 0.22, and suggesting reduced or non-oxidized environment. Calculated geothermobarometry resulted in depths of approximately 50 kilometers to 100 kilometers. Heterogenesis of the peridotite consists of partial melting and metasomatism. The mantle below Harrat Uwayrid was subjected to similar large-scale events of the Arabian plate, and the study periodic xenoliths exhibit generally similar degrees of partial melting, similar oxidation state, and metasomatism in comparison to the other similarly aged Western Arabian Harrats. Further recommendation for the future are perform point counting as a method for mode classification, which can complement the norm calculation that was done from the major rock elements, and provide dependable XRD and ChemScan results, because currently still calibrating between for usage in igneous rocks. Isotope analysis, correlations of the petrogenesis to the major tectonic events in Saudi Arabia, and also application of the study methodology, hopefully, to other less studied mantle periodicite xenoliths from Cenozoic age Harrats in Western Saudi Arabia. These are selected references. Thank you. I know I'm not. Thank you for staying to the presentation. I know I'm not outside of the forest yet, but I would like to take a few minutes from the time to give several acknowledgements. So Alhamdulillah, all praises to Allah that He has provided me the opportunity to study here, and also given me the strength to finish the study itself. And also peace and blessings be upon our Prophet Nabi Muhammad sallallahu alaihi wasallam. And acknowledgements I would like to extend to King Fahd of KFUPM, to Dr. Zumo, the Dean, previous Dean, and now the current Dean, Professor Humaidan, for their the opportunity they have provided me here. Also to the CPG, the beloved environment that is created here is excellent. The staff, the lecturer and everybody has shown an example of how to be a scientist, research lecturer, and also the fellow students would have great passion. This also extends to our previous and current chairman, Dr. John Humphrey. Thank you very much. To our graduate coordinator, Dr. Kaka. Also to my esteemed thesis committee, especially Dr. Scott Wattam, which knowing that I had no previous or minimum background in igneous petrology, accepted me to be his student, and then we worked on the project, and hopefully a nice project. And thank you again for Dr. Amau, Dr. Ardi for accepting the position of the committee members, and also your valuable inputs in my thesis, and also to the support for my parents and relatives in Indonesia for asking me to pursue the master degrees, and also Mr. Mutasim Osman, which accompanied me, and Dr. Scott, as well as again CPG colleagues like Bandar and Abdullah, which helped me with XRD and ChemScan, but unfortunately this time not included yet in the presentation, but hopefully in the future. Also Jin Seo from Korea University, and Sisjan from Edinburgh University for the help in EPMA analysis and help with the calculations, adjustments to the calculations. I thank them very much for their input. The Indonesian community here in Dhahran, especially my fellow colleagues here, students, which accompany me here until now, and the new faces. Thank you very much for being the family here. Also other community like the staff and the lecturers. Also special mention to Muhammad Salam Johari and my friends in the MAM. Also the general students of KVPM, which we interacted throughout me being here, and finally my family, my wife and my daughters, which have have a lot of patience, during my study here. I thank them very much. I cannot repay them enough. And Saudi Arabia, I would like to thank the king and also the current prince, and also Saudi Arabia generally for having the warm welcome and having me living here for this couple of years. With that, I close this presentation. Thank you very much for listening. And I believe that now will be the main part. I will give this back to Dr. Scott.
Okay. Everybody here? Yeah. Okay, thanks, Iskandar, for a great presentation. Excellent outlines, figures, and I think you explained everything very well. So we're going to take this opportunity now for general questions from anybody out there. John?
And nice to see a good showing from the Indonesian mafia. Iskender, that was a fantastic presentation. I tell you what, I'm fascinated. Absolutely fascinated by this stuff. Not enough to be an igneous petrologist, but fascinated. And some of us were just standing in the Mantle the other day in Oman. So this kind of comes from. So I got a couple of questions. The first question is just a conceptual question that I haven't, thought about this stuff ever, but so when you show your ternary diagrams for these ultramafics, and you've got olivine and OPX and CPX, so what actually controls for the pyroxenes which you're going to get, the OPX or the CPX? Is it just thermodynamics? Is it composition of the, I don't even know what I'm talking about, but it was, why do you get predominantly Harzburgites and Lerzelites and not the Wehrlites, let's say?
Okay, you have two questions you mentioned.
Well, that was one.
Oh,
So
one.
that's just a conceptual one. Then
Oh.
I've got more of a geological one.
Okay, so yeah, as far as my reading, hopefully correct, that the Lerzolite and Harzburgite, they are here from the beginning of the creation of the Earth itself, scientifically. So from the meteorites, the chondrites. So the chondrites that are proposed as the origination or the origin of the Earth itself is composed of olivine and pyroxene.
So just what we got allotted at the beginning of
That's
this,
right.
of this
Yeah.
whole
And
system.
then
Okay, that's
due to differentiation, the heavy elements go to the core, and then the lighter elements are differentiated to the top of the.
okay, that's cool. So when we think about this whole system here, where we've got essentially a ridge triple junction at Afar, we've heard all about the Harrats in Saudi Arabia. I assume there's matching ones on the Nubian Shield. Okay.
Yes, it
Yes.
should be, yes.
Okay, and then of course, then we look at the East African Rift, right? And and there's volcanism going on there. Now, have people studied the xenoliths in the East African Rift?
Yes, this is a very good. Oh, sorry, doctor.
No, okay, so I was just sort of going to follow up and say, number one, I know there's carbonatites that are being erupted there, but there are old rift sequences around the world that are exposed, and there are intercalated volcanics in and amongst the rift clastics and stuff like that. Have people studied those, say, old rift systems, whether it's like the Rio Grande Rift in the US, or I think of one specifically in Morocco where we've got an inverted basin there in the High Atlas. And so I'm just wondering have people looked for mantle xenoliths in these old rift settings? That's all. Thanks.
Okay. Thank you, doctor. Thank you for the question. I'm sorry, I forgot at the beginning. I should have said thank you. Thank you for very good points. Yes, and this question that you answered, you asked, doctor, we discussed with Mazin, which is he was from Sudan, and he mentioned that there are like similar like Harrats or similar Harrats in his area, Sudan, but maybe, and also discussed this with Dr. Scott, it's most probably no xenolith information or maybe Harrat's information in the Eastern Nubian Shield due to less or no studies on these subjects. So still maybe a lot of opportunities to do study on that side of the Nubian Shield. And as for the second part is that, yes, there are studies, as far as I know from my reading, hopefully again, this is the correct interpretation, that there are studies on mantle peridotites from the old rifts, but they are classified not as xenoliths, but I think they are classified as abyssal, tectonic peridotites, which are caused, or they are tectonized or tectonically moved up to the surface rather than this, which are brought by the magmas. Therefore, these are characterized as relatively or extremely fresh, whereas these peridotites are relatively altered. And but for those peridotites, they have nice correlation between each other peridotites, because these xenoliths only have like fragments, so we cannot visualize their spreading on the outcrop. So I think hopefully that there are studies, doctor, but I need to recheck on the locations that you mentioned.
Thanks, really great job. I
Thank you very much, Doctor.
Okay. Yeah. No, I have something general.
Okay, thank you, Mr. Okta, for the presentation. It's very amazing. I mean, this is the first time I see like a very fresh peridotyte. Usually in my lifetime, I encounter this tectonized peridotyte, which is like heavily metasomatized. We can see serpentinite and magnesite everywhere. So my question is regarding the metasomatism. You said that it's because of the silicate. It's not because of the silicate melt and carbonatite melt, but instead it's a result of the H2O interaction. Is it right?
Yes, correct. Yes, correct.
Okay. What proof do you have to say such thing? I mean, do you have like the indication from petrographic such as serpentinite, or could you move to the slide where you explain us about the wearlite?
The Uwayrid, okay.
Yeah, the wearlite.
Uwayrid. Thin section.
Thin section, the one with the brown, yes, the brown color.
Yes.
Is it the brown color represent eadimsite or other minerals within the olivine?
Okay. So the two questions, right?
Yeah.
Thank you for the question, Faris. I think you're the expert in this rather than me. But to answer your first question, to elaborate how we concluded that the most probable agent for the metasomatism are H2O rich fluids is that in Dawn's study in 2001, she mentioned that the depletion, a relative just moderate depletion of neodymium and zirconium, also hafnium element, and the appearance of phlogopite in the thin section, the phlogopite mineral, that is most probably the result of subduction related fluids which brought the elements, and that therefore silicate melt, I colored this in blue because this is indicated by high abundances of rubidium and barium, but here we see the rubidium and barium are depleted, so therefore that's not silicate melt. And carbonated magma is characterized by the very high depletion of neodymium and zirconium and hafnium, whereas here it's relatively moderate. Therefore, that's why we constrain this into metasomatism by H2O rich fluids, and that is further supported in the study of Bluestagen and Caliwood. So hopefully this gives my argument clearly. And the second question for the wearlite, honestly, I only understand wearlite from the conception that it was let's say fertilized using the. I still don't understand fully about this terminology, but it was refertilized by most probably carbonated melts or melts. So the cause of why these olivines have this characteristic brownish color, I myself unfortunately don't have the answer. Hopefully we can work together to find out this answer. Okay, thank you very much. Hopefully this satisfies your question.
Can you go to your recommendation slide? I don't have any question, by the way. It's a nice presentation, but your recommendation
Okay.
slide.
Okay.
Yeah, so in your recommendation, you said to provide dependable XRD. I decided to raise this so that other students can benefit. What specifically was the problem you faced with the
Yes.
XRD?
Okay. Okay, the two left lectures in here, so I'm under pressure. Immediately under pressure. Okay, thank you, Dr. Amang, for your question. I mean, for the request for the explanation. What I meant from provide dependable XRD ChemScan is because the XRD and ChemScan labs here are familiar with the igneous rocks generally. Therefore, me myself being also unfamiliar with the steps on how to analyze properly, correctly these igneous rocks, like, for example, the grinding, what type of grinding machine that we need, and then also the size of the particles.
No, but those are standard, like grinding for XRD is not an issue. I understand if you, because this is a very strong criticism, really. If it is the issue of having like the mineralogical database, we can specifically purchase something. But again, look at it this way, maybe for the past 4 years, you are the first person requiring such database. So, and these are very expensive. So that would have been reasonable, you understand? Because from my point of view, the XIV is working very well.
Oh, yes.
I'll give you an example. When we purchased the system, we purchased not copper tube, we purchased the cobalt X-ray source for anybody doing shale mineralogical characterization. There's been no single use of it since it was purchased. So that's why most of the time when we are discussing about the new purchase, we try to do things that will be utilized from time to time. But if you had said, for example, that no data was generated or acquired for you, it's a different thing. The technicians are not supposed to understand anything research you are doing. They are supposed to help you acquire correct data. You need to figure out how to interpret your data yourself.
Oh,
Yeah.
Thank you very much, Dr. Amau. I might have miscommunicated this. What I might provide dependable is regarding again to the steps that myself needed to do to produce the dependable XRD and ChemScan results. So I might have miscommunicated this point, but yes, you are correct. The XRD and the XRD works very well. Also the ChemScan also very well also, but maybe for the ChemScan we needed just slight calibrations with the minerals.
You need to hear my comment as well. Well, in this model, that is for all, by the way, we have the certified for all segmented rocks. Alhamdulillah, but for the igneous rocks, again, I told you certified issues, and that depends on you at this moment, because we have not yet actually created certified for igneous rocks. Maybe in the future. So if there is anything that you need, is from you. Provide us a permit from the XRD, then we analyze it together. At this moment, maybe in the future, we can build the SIP library for igneous rocks.
Okay. Once again, thank you, Dr. Amau and Abdullah, for the clarification. And again, I just want to clarify, this is maybe my mistake in miscommunicating this. It should be that, I mean, dependable results because my steps on using the XRD and the ChemScan.
So I have a question.
Yes.
I noticed that you use the geochemistry class. I saw Harrat diagram and this spider diagram as well. I see Harrat diagram. There are some kind of elements that have kind of good correlation, but the others actually don't. How do you explain these variations?
Okay, so what do you mean? Is this slide?
Yes.
So from previous researches and also current researches, of course, that in peridotites, specifically aluminum oxide, calcium oxide, sodium oxide, and titanium oxide, these are, let's say, incompatible elements. Okay, so they prefer to, they have this partition preference to insert or go to the melt when partial melting occurs in this peridotite. So therefore, when magnesium oxide increases due to the residuum or the leftovers of the melting, which are olivines, these aluminum oxide, calcium oxide, sodium oxide, and titanium, they are released from the peridotite and they come into the melt, and that's why the melt of basalts are rich in these elements, whereas the residuum or the leftover of the peridotite, which are Harzbergites, are dominant with olivine and minor clinopyroxene. So it's related to the partial melting. So these elements have partition partition coefficient, which prefers to go to the melt. That's why they go to the melt when partial melting occurs. So that's why they have good correlation with MgO. So it's related to the partial melting. Yes.
and no effect on this iron oxide and silica there, because no correlation there.
Yes, for silica oxide, I'm not quite sure, but it still does to a certain degree. We see that this random maybe trend, although silica oxide is less pronounced because again silica still goes to the melt and will be brought by the melt towards the surface. Also here in iron oxide, but chromium oxide, phosphorus oxide, and the others, I'm not sure about this in whole rock chemistry, but later in mineral chemistry in clinopyroxene, they have different behaviors regarding their correlation.
This spider, the other question, this spider diagram, did you use like 6 samples? Are these the whole 6 samples that you used, or just the average of the from each section?
Okay, so these are, so from the 18 samples that were analyzed, only 11 were had major whole rock chemistry because of the size. So the other 7 were very small, tiny, so they couldn't be made into pucks to be sent for analysis. So we did use the 11, and here we have at the top around 5, and we have the first 6 here at the bottom for the 4 Harrat Uwayrid samples, and they are only, so I used each and every one of the analysis for each sample because each sample only did one analysis for the major rock composition.
I guess 6 samples, right?
These are different. So these I categorize this based on the beginning. This one. So here I divided the samples which have high LREE and the one that have flat LREE, and based on that I divided also the spider diagram. So half were used in the top one, and half was used on the bottom one. Okay, thank you very much, Abdullah.
Thank you. Thank
you.
Well done. No, stop. I'm sure nobody will ask. So
Can I just ask a couple of quick questions? I never noticed these high field strength element depletions before, and it's interesting that they're in Hart's brigades. No, go back to the your rare earth element plots, or actually the primitive mantle.
Okay. So
Yeah, this one right here at
Yep.
the top. So they're actually Hart's brigades, which are showing the high field strength elements. So I mean, yeah, this is a subduction signature, and actually in the lavas themselves, we got isotopic evidence of subduction enrichment. So it's been contaminated to some extent. So that's very interesting. I didn't notice that before. And one other thing, with respect to with respect to partial melting, there's a very simple formula based on chromium spinel. So chromium spinel, the ln 10 plus 25.
oh yes, sir.
So did you mention that?
Yeah, I did mention
And
briefly,
what are the comparisons?
but very
Whole rock.
briefly here. Yeah, here this one here.
Oh, I see.
Yeah,
Okay, I
so
didn't see that.
Is this
Okay.
one to the right side? But so they compare nicely the calculation from the spinel with the general results of the whole rock and mineral chemistry, except for one sample here, which here is 4%, and the other 2 are high.
Okay. So
Whereas the
very-
others, they
very
are
well, yeah.
they compare relatively nice.
Mhm.
yes.
Okay, okay. Oh, we have a closed session. Okay, all right.
Finally,
Thank you.
Thank you very much. 10 minutes. Yes.
yes. Yeah, 5 minutes to 10 minutes.
Okay.
Oh, okay. I didn't know the time constraints.
We don't have one.
Yeah.
Thank you, Dr. Amal.
It's a very nice.
Yeah, thank you very much. Again, I'm sorry for the miscommunication.
It's not, trust me, it's fine. I actually like criticism because how do we know about a technician? I was hoping you tell me technicians misbehave, actually, because it's not that. It's different.
Yes.
So should we?
Yeah, I guess
Yes,
it's better, right?
it will be in 10 minutes.
Are we supposed to ask questions now?
Yeah, you can ask him questions.
Okay.
Session, but Normally, this is the time we say, oh, pass or. he's not
Yeah,
passing or
okay,
something.
okay. I wasn't aware of the time
Okay.
constraint. So anyway, yeah, we better leave. We'll find another room.